Hello there, we're going to have a look here at how we could come up with the formulae that we use for permutations and combinations. So we start off by talking about permutations and try and derive the formula for that first of all. Basically a permutation, if I talk about the number of permutations of something happening, it's, as it says here, the number of ways of arranging a set of objects chosen from a larger set where the order matters. So when we look at an example in a second, that hopefully will make a bit more sense. But the notation that we use for that you can see is NPR. So that would be the number of objects that we were choosing from, and that would be how many we're actually choosing. So we're choosing R objects from N, and the order matters with permutations. That's the big difference between permutations and combinations. So let's have a look at the idea behind this and see if we can come up with a formula. So how many permutations are there of picking a 2-letter code from these 6? So as I said, the difference with a permutation is that if I'm picking a 2-letter code, then AB would be counted as something different to BA. And obviously that's true with most, a lot of scenarios. For example, if you were working out a password, the order that you type things in would be important. So let's imagine how many ways you could do that. Well, obviously, we could have the A being combined with the B, the C, the D, the E, or the F. So the A has got 1, 2, 3, 4, 5 things that it could be combined with. And the B also has 5 things it could be combined with. It could be BA, because that's a different order, so I need to count it separately. BC, BD, BE, BF, and so on and so forth. So I've basically got 6 different letters, and each of those letters has 5 other letters that it could be combined with, because it can't be combined with itself. So ultimately, there will be 6 times 5 permutations that could arise. Okay, 5 with the A as the first letter, 5 with the B, 5 with the C, D, E, F. So therefore 6 lots of 5. And let's also, to try and help us see the formula and the derivation for it, let's think how that could be rewritten. And we're going to think particularly about the use of factorials here. So we need to think back to when we first covered this with the idea of the binomial expansion. So if we've got 6 times 5, we're basically thinking we've got, for factorials, 6 times 5 times 4 times 3 times 2 times 1, but I then need to cancel out the 4 times 3 times 2 times 1, so that's going to be 6 factorial divided by 4 factorial. That would then just leave me with the 6 times 5. So we'll come back to that later. That's going to help us to find the overall formula. Let's now think of the same thing again, but exact same letters, but let's imagine now picking a 3-letter code. So for example, it could be ABC, or it could be ABD, and so on. Well, let's then think of that code. How many ways are there that the first letter could be chosen? Well, there's 6 possible first letters. It could be A, B, C, D, E, or F. Having chosen that first letter, how many ways are there that the second letter could be chosen? Well, obviously 1 letter is already gone. Whatever I've chosen as being the starting letter has now been taken, so there's only 5 letters left. So there's 6 letters that could be used for the first, 5 for the second, and then 4 letters left for the final letter of the code. There's only 4 letters left. So 6 times 5 times 4. And again, as factorial notation goes, that's 6 times 5 times 4 times 3 times 2 times 1, but I then need to cancel out the 3 times 2 times 1 part, so that will be 6 factorial divided by 3 factorial. You can see this is going now. 4-letter code, we've got 6 possibilities for the first letter, 5 for the second letter, 4 for the third letter, and 3 for the final letter. That is 6 factorial divided by 2 factorial. Let's just look at one example when we've got some extra letters in there. If I was going to try and choose the permutations for a 3-letter code from these 8 letters, then there would be 8 choices I could make for the first letter, there would be 7 choices for the second letter, and there would be 6 choices for the final letter. So 8 times 7 times 6, or 8 factorial divided by 5 factorial. Let's look at all those 4 examples again and see if we can see where the formula is going to come from. So the number of permutations choosing 2 letters from 6 was 6 factorial over 4 factorial. 3 from 6 was 6 over 3, and so on. Well, clearly, whatever number I have up here is the number that I'm taking at the top, the factorial at the top. How am I getting the number at the bottom? Well, hopefully you can see that it's this number subtract this number here. 6 take away 2 is 4, 6 take away 3 is 3, 6 take 4 is 2, 8 take 3 is 5. So if we put that together as an overall formula in the form NPR, we could say that it's going to be n factorial divided by n minus r factorial. So that's the derivation for a permutations. And there is a permutations button on your calculator, but it's useful to know the formula in case you need to use it. Now let's have a look at the combinations. So the difference with combinations is, again, I'm choosing, if I write it like this, I'm choosing R objects from N objects, okay, but this time the order doesn't matter. So for example, if I chose an A and a B, I wouldn't need to count B and A in that order as being separate. They would be the same thing. So that's the fundamental difference between permutations and combinations. So let's have a look at an example and try and come up with our formula. So let's think about the number of combinations there could be of picking 3 letters from these 4, A, B, C, and D. So if you think through the combinations, I've deliberately chosen a low number of letters so that we can easily work them out. Obviously, if there's lots of letters, this starts to become very complicated to do by hand, and that's why we need the formula. So A, B, C, D, well, what could it be? It could be A, B, C, it could be A, C, D, A, B, D, and B, C, D. So there are basically 4 possible combinations that I could get when I'm choosing 3 letters from 4. But notice the difference is that ABC or BAC or CAB, any of those, I don't count those as different ones, which I would do if it was permutations. So now what we're going to do is we're going to try and work out the formula for these combinations, but we'll do it by looking at the permutation formula we've already worked out. So we'll be thinking of the fact we know how to do permutations, and we can then work out the combinations formula. So let's have a look at this. If you imagine, let's just take the ABC for the time being. So in the permutations formula, then all of the different arrangements of A, B, and C would be counted. So if I've got the letters A, B, and C, basically I would be counting that 6 times for a permutations question. But for combinations, I only want that to be counted once. I don't want the order to matter. So there's 6 ways that the A, B, and the C could be written, 6 ways the A, C, and D could be arranged, 6 ways for that, 6 ways for that. And another way of thinking of 6 ways is that that's the same as 3 factorial, 3 times 2 times 1. And that, again, hopefully makes sense. There's 3 choices for the first letter, 2 choices for the second letter, and 1 choice for the third letter. So basically, if we imagine doing 4 choose 3, we are doing the 4P3 formula, but we've counted things more times than we wanted to. We've counted each combination 6 times, so we need to divide this by 6 to give us the true number of combinations. And so then I could write that potentially as 4P3, which we worked out before is 4 factorial over 4 minus 3 factorial, and then I've also got this additional 3 factorial on the denominator coming from there. Okay, and that hopefully gives you a pretty good indication of where this formula is coming from. Let's have a look at one more example. So let's say we wanted to work out the number of combinations of picking 5 letters from this list of 8. So 8 choose 5. So again, if I was thinking of the permutations, obviously there's 8P5, but that would then mean that each combination of 5 is being treated as 5 factorial different orders. So for example, if I had A, B, C, D, E, then that's also for permutations having A, B, C, E, D, and every single different arrangement of that. Well, I want to get rid of all of those if it's combinations. I don't want them. So I will do 8p5 and I will divide it by 5 factorial. And that, again, if we write it with the formula notation we had before, 8p5 we said was 8 factorial over 8 minus 5 factorial, and now we have an additional 5 factorial on the denominator. So now if we put that together, we can see that basically it was NPR divided by R factorial. If I just go back, you can see that it was always this number here. It's the factorial of that number that we were always dividing by, in addition to the normal NPR formula. So I'm dividing by R factorial, and if I condense that by actually saying what NPR is n factorial over n minus R factorial. So n factorial over n minus R factorial, that's NPR, and then the R factorial is this bit here. So that is the formula that we use for n choose R, or the number of combinations of R objects from n objects.